Morning. Nayak, you will say up to what I discussed. Nayak, are you getting my voice? Am I audible? So, up to what I discussed? CO2 graph. CPCV started. CPCV, okay. Somebody is saying CO2 graph. Okay, CPCV gamma mixture, gamma. Gamma also over. CP minus CV is equal to no. Okay, CP minus CV capital R I discussed. Small CP minus small CV R by M that I discussed. Okay, this is one question also we have done. Okay, so I think it is a last. CP minus CV is equal to R by M. Okay. Then now gamma we will discuss. So ratio of molar is specific heat that we represent by gamma. So gamma is what? Gamma we define CP by CV. So this is also called the adiabatic constant. We will discuss in adiabatic process. So ratio of the molar specific heat gamma, that is a CP by CV, and we know that CP always greater than CV. So gamma will be always greater than 1. Okay. Then monatomic gamma, what you will get? So if they are not given about the vibration, we will always ignore the vibration. So monatomic directly, maybe somebody has mucked up also. Gamma of the monatomic CV is what? 3R by CV is the 3R by 2. CP of how you will get? By adding the R. So CP of monatomic is what? 5R by 2. CV 3R by 2. So 5R by 2 upon 3R by 2. So R by 2 get cancelled out. What you got? 5 by 3, that is equal to 1.67. So gamma of monatomic gas is the 5 by 3. Diatomic gas. So CV is the 5R by 2, CP is the 7R by 2. So what you will get? 7 by 5. So gamma is equal to 7 by 5, that is equal to 1.4. And number 3, polyatomic. So all these value I am writing by ignoring the vibrational. Okay. So gamma of polyatomic. So gamma CV is the 3R. Then CP will be 4R. So 4R upon 3R, what you will get? 4 by 3. Completed. So who will say, suppose I am saying polyatomic gas has X vibration mode, X vibrational mode. What is the gamma of the gas? If polyatomic gas has X vibration mode, what is the gamma of the gas? If polyatomic gas has X vibration mode, what is the gamma of gas? So in the last class I discussed 1.33x. How 1.33x? Okay, so what is a CV? What is a CV? If polyatomic gas has X vibrational mode. Then CV I said 3 plus x into r. Remember 3 plus x into r. So CV is the 3 plus x into r. Then what is the CP you will get? You will add r in that. So when you will add r, what you will get? 4 plus x into r. Okay. Then what is the gamma? Gamma will be CP by CV. So that is 4 plus x upon 3 plus x. Okay, so suppose x I have given the 3, so 4 plus x, 3 vibrational mode, so 4 plus 3, 7, 7 upon 3 plus 3, 6. So 7 by 6 gamma you will get. Okay. Okay. Now in a chemistry, maybe you have learned molar mass of a mixture. So molar mass of a mixture formula may be N1 M1 plus N2 M2 upon N1 plus N2. You have learned or not in chemistry? Molar, if we are mixing the 2 or more gases, then we can calculate the molar mass of the gaseous mixture. Similarly, we require sometimes what? CP mixture, CV mixture. So when we have the gaseous mixture, they can ask what is the CP mixture, what is the CV mixture. So similar formula you will get. How you have learned, what you have learned for the molar mass. So CP mixture we can say what? N1 CP1 plus N2 CP2 upon N1 plus N2 dot dot dot. Similarly, CV mixture, that is equal to N1 CV1 plus N2 CV2 upon, okay. Then by that way we can get the gamma mixture also. Gamma mixture, what I can write? CP mixture upon CV mixture. Completed? So this is the easy way to calculate the gamma mixture, because otherwise some direct formula is also there for the gamma mixture, but that formula is little bit lengthy and maybe you will mug up, so then you will get confused, so you get wrong answer. So gamma mixture is easy to find by using the CP mixture upon CV mixture. So if they have given the gaseous mixture, so first we will only find CV mixture. Okay. Why unnecessary we have to apply the 2 different formula, more calculation? What we will do, if they are asked, they have given the gases and they have given the mole, then we can find the CV mixture. How? N1 CV1, N2 CV2 upon N1 plus N2. Okay. And CV we mugged up. CV we directly remember monatomic 3R by 2, diatomic 5R by 2. So first we will calculate the CV mixture. After getting the CV mixture, directly you will get the CP mixture is equal to what? CV mixture plus R. Why we have to unnecessarily calculate the N1 CP1 plus N2 CP2? Getting my point or not? So only we will calculate CV mixture. It will take one line, then CV mixture. After getting the CV mixture, CP mixture I can say CV mixture plus R. After adding R, you will get the CP mixture. Then divide both, you will get the gamma mixture. Okay. So both moles and gases they have given, then it is easy to go through this. If you want to mug up, then I will write the formula for the gamma mixture. But if moles you know, it will be always time saving. Okay. So that another formula is what? N1 plus N2 upon gamma mixture minus 1, that is equal to N1 upon gamma 1 minus 1 plus N2 upon gamma 2 minus 1. But now you can see it is difficult to remember, and if you can remember, then directly you can apply, and calculation will also be little bit lengthy, but it will be easy. Okay. So when you know the moles and gases, then it is easy to find CV mixture. After finding CV mixture, find CP mixture, then you can get the gamma mixture. Okay. Completed? Okay. The 2 relation you have to remember. Suppose I have not mentioned the gas, like monatomic, diatomic I have not given. I given the degree of freedom of a gas. Only degree of freedom of the gas I have given, and I need the gamma. I need gamma if I have given the degree of freedom. Okay. So gamma formula, we know that gamma is equal to what? Cp by Cv. So Cp by Cv. So Cp I can say Cv plus R by Cv. You can write or not? Okay. This has done. Okay. Then you cross multiply, so you will get what? Cv, gamma Cv, Cv plus R. So Cv by solving you will get what? R upon gamma minus 1. Remember this formula for the Cv directly. Maybe they have given the gamma. They have not mentioned the gas. So Cv how we can find? Cv is equal to R upon gamma minus 1. Okay. Then Cp what you will get? Cp by Cv is equal to gamma. Then Cp what you will get? Gamma into Cv. So gamma into R by gamma minus 1. This is the Cp. Okay. And Cv is equal to what? Fr by 2. Already we have learned Cv is the Fr by 2. If you put Fr by 2, so Cv is the Fr by 2 is equal to what? R by gamma minus 1. So R and R cancel out. From this gamma what you will get? 1 plus 2 by F. So these three relation you have to directly remember. Cv in the terms of gamma, Cv is equal to R upon gamma minus 1. Cp, gamma into R upon R gamma minus 1. And gamma and degree of freedom relation is what? Gamma is equal to 1 plus 2 by F. Understood? Completed? If you are getting confused between 1 plus F by 2, 1 plus 2 by F, so you can think F is what? F will be more than 3, so 3 by 2 you will get gamma more than 2. But we know that maximum gamma of 5 by 3. So that's why it is a 1 plus 2 by F. Okay? Completed? Okay. So if it is a problem, suppose they are saying the diatomic gas. They are saying diatomic gas, they are asking Cv. They are saying the diatomic gas, but in the bracket they have given gamma. They are saying diatomic gas, but in the bracket they have given gamma. Okay. So, like example you can write. Okay, so find Cv of the diatomic gas, gamma is equal to 9 by 7. So diatomic gas, if I mention, so you will think that Cv directly we have marked up for the diatomic gas. Cv is the what? 7 by 5. But if they have given the gamma, so gamma if they are writing, it means gamma is the result of all degrees of freedom we have included, means they have included the vibrational also. Okay. What we marked up, we have ignored the vibrational, then we got the gamma is equal to 7 by 5. But if they have given the gamma 9 by 7, so we have to use this gamma. Getting my point or not? So we will not write Cv is equal to what? Cv for the diatomic gas is what? 5R by 2. Getting my point or not? So we will use the gamma. So Cv what we can write? Cv is equal to R upon gamma minus 1. Hare, yes or no? So what we have marked up? We have marked up for ignoring the vibrational. Okay, ignoring the vibration. But here they are saying what? They have given the gamma. It means we have to take that gamma. Okay, so Cv we can say R upon gamma minus 1. So what is the Cv? You will get R upon 9 by 7 minus 1. So what you will get? 7R by 2. Okay. Understood? Completed? Okay. Next. Suppose I am saying mixture of monatomic and diatomic gas gamma is equal to 1.5. Okay, then find ratio of their mole. So here I have given the gamma mixture and two gases are mixing, monatomic and diatomic, but they have not given the moles of the monatomic and diatomic gases. So they are asking the ratio of the moles. Okay. So suppose I am taking the mole of the monatomic is N1 and mole of the diatomic is N2. Gamma mixture we know. So which formula we can use? So suppose we know that CV mixture formula we have what? N1 CV1 plus N2 CV2 upon N1 plus N2. Yes or no? Okay. And CV in the terms of gamma directly we know CV is equal to R upon gamma minus 1. CV is equal to R by gamma minus 1. So this I can write as R upon gamma mixture minus 1. Okay. CV1 monatomic gas. So what you will write? N1 into 3R by 2 plus N2 into diatomic gas CV 5R by 2 upon N1 plus N2. That will be equal to what? Gamma mixture I gave 1.5. So 1.5 minus 1, 0.5. 0.5 means 1 by 2. So what you will get? 2R. Are yes or no? Okay. Now R get cancel out. Now cross multiply, then what you will get? 3N1 by 2 plus 5N2 by 2 is equal to 2N1 plus 2N2. Actually, there was that day some problem was there in a live class, so that's why they have not recorded it. Okay. Now this N2 you can shift here. So what you will get? 5N2 by 2, 5N2 by 2 minus 2N2. That is equal to 2N1 minus 3N1 by 2. So this you will get what? N2 by 2. This what you will get? N1 by 2. 2 and 2 cancel out. What you got? N1 is equal to N2 or N1 upon N2 is equal to 1. So ratio you got 1. Completed? Okay. So they, by this way, maybe they will give the direct gas, they will give the number of mole also, like monatomic gas, diatomic gas, 2 mole, 4 mole, they are mixing. What is a gamma mixture? We can use the formula. First we will calculate the CV mixture. After that we will add the R, you will get the gamma mixture. That is a problem. I have to see that it is recorded in my app or not. If it is a recorded, then something we can do, otherwise not. I will check, okay? Completed? Okay. So one more you can do. Suppose 2 moles of helium mixed with 4 moles of oxygen. Find gamma mixture. Tell fast. What is the answer? Tell fast. Anybody got answer? So first we will calculate the CV mixture. CV mixture we can say N1 CV1. What is the mole of the monatomic? 2. CV1 means CV of the monatomic. So monatomic CV is what? 3R by 2 plus N2 CV2. N2 CV2 means 4 and CV2 will be diatomic. CV is what? 5R/2 upon N1 plus N2. N1 plus N2 means 2 plus 4, that is 6. Okay, this 2 and this 2 cancel out, this and this cancel out. So what we got? 5 to the 10 plus 3, that is 13R/6. So CV we got 13R/6. How 13R/2? Then CP mixture, what you will get? CP mixture is the CV mixture plus R. CV mixture plus R. When you add R in that, so what you will get? 13 plus 6, that is 19. 19R/6. Now what is the gamma you got? So gamma will be equal to CP mixture upon CV mixture, that is the 19/13. Okay. Completed. How 19? Arre, you don't know the addition. You'll say what? CP is equal to CV. CV is the 13R/6 plus R. So take the 6 LCM. So what you will get? 13R plus 6R. So that's 13 plus 6 is equal to 19. Okay. Surya, got it? Okay. Now next is the Joules law. So this is not the new law. We are using the Joules law. Okay. So what is the Joules law? So he said that work and heat are equivalent. Already we are using this. Work and heat are equivalent. If I want to produce the 1 calorie of heat, if we want to produce 1 calorie of heat, then how much work is required? If you want to produce 1 calorie of heat, how much work is required? 4.2 joule work is required. So we know that 1 calorie of heat, if you want to produce, then we require the 4.2 joule of work. Yes or no? So that 4.2, this value is called the mechanical equivalent of heat. And if you want to calculate, so this we represent by, this is the J, and J we say mechanical equivalent of heat. And that J, how we can find? J is equal to W by Q. Means work upon heat, if you divide, then you will get the value of J. Okay, so J is equal to W by Q. Okay. Okay. So this already we know that we are using it, this relation also, 1 calorie is equal to 4.18, but numerically we use the 4.2 joule. Okay. And if suppose you know the work, you know the heat, then how we can calculate the mechanical equivalent? That J is equal to what? W by Q. Okay. Completed. Okay. So now some problem. Suppose we have the ice block. Any ice block is falling from the height h. Any ice block is falling from the height h. As it is falling due to the air resistance or what, its energy is decreasing, and that energy is going in the form of heat. Okay. Practically what will happen? Some energy will, like it is melting, so when it is a melting, so some drop, they will have the potential energy. But numerically, suppose they are saying ice is at the height h, it is falling, then whole mechanical energy converted into the heat. Whole mechanical energy converted into the heat. Due to that, ice melt completely before reaching to the ground. I repeat again, then any ice block we have at a height h. Okay. When it started falling, So all of its energy converted into the heat. Okay. Then, and due to that heat, ice melt completely before reaching to the ground. Okay. Then what is the height h? What is the value of h? Understood? Everybody got the problem or not? Okay. So what I'm saying, it is at the height h, and it started falling. So it lost its energy completely and in the form of heat. Then due to that heat, ice melt completely before reaching to the ground. Then what is the value of h? Okay. Question if you want to write, you can write. Now, if suppose I am asking how much heat produced. So how much heat produced? They are saying the heat produced is equal to the all energy goes in the form of heat. So heat produced, we can say what? What is the energy it has? It has energy mgh. Due to the height, it has energy mgh. Maybe option. Suppose they are only asking the heat produced. So heat produced, maybe they can only give mgh. Otherwise, if they are giving the option like this, mgh by j, it means the answer they are given in calorie. Maybe they can give the option. Suppose they are only asking what is the heat produced. So heat produced is the energy. Energy is what? mgh. So that mgh you will get in joule. But maybe option they are given in calorie. So what they will give? mgh by j. What is the j? Mechanical equivalent. Understood? So if this option is there, like they will give mgh into j, mgh by j. Okay. So which option you will write? mgh by j. This will be equal to the heat produced. Everybody got or not? So now, but in this problem, what I'm saying, whole energy converted into the heat, and due to that heat, ice melt completely. Okay. So we can say heat produced is equal to what? mgh. That you will get in joule. Okay. M you will put, G you will put, into S you will get in joule. Okay. Now that heat is melting the ice. So for the melting of ice, how much heat required? ml. Heat for melting is what? ml. That ml is coming from mgh. So we can say what? mgh will be equal to what? M into L. Now M and M cancel out. Yes or no? Then H, what you can write? L by G. Now, latent heat of melting of ice, we know that 80 calorie per gram. But G value, what you will use? G value, you will use 9.8 or 10, suppose. G value, you will use 9.8 or 10. So we are using the G in MKS. But L value, we are neither the MKS nor CGS. 80 calorie per gram. 80 calorie per gram. So calorie per gram, you have to convert into the MKS unit, joule per kg. So conversion factor I said in a class 4200. Okay. Then what you will do? 80 into 4200 upon G I am taking 10. So this and this cancel out. So what is the H you got? 8 to the 16, 8 to 32. So 33600 meter, or we can say H is equal to 33.6 kilometer. Understood? If suppose they are saying half of the energy converted into the heat, then heat produced, what you will take? mgh by 2. So according to the problem, we will take the heat produced. If that heat is melting, so that heat we will equate with ml. Okay. Okay. Next problem. If suppose you have one lead bullet. Okay. It is moving with a velocity v. A lead bullet I have, it is moving with velocity v. It hit the wall. And it completely stopped. So heat produced is equally shared by the wall and the bullet. I am writing the problem. If bullet initial velocity is 200 meter per second and it hit the wall and stop completely. Heat produced is equally shared by wall and bullet. Then find increase in temperature of bullet if specific heat of lead that is equal to 125 joule per kg degree C. So if the bullet has initial speed, I have gained 200 meter per second and it hit the wall and it stopped completely. Heat produced is equally shared by the wall and the bullet. Then we have to find the increase in temperature of the bullet. So here bullet has the energy how much? Half mv square. Initial problem, it has the energy mgh due to potential energy. Now here due to the velocity speed of the bullet, it has the energy half mv square. When it hit the wall, it stopped completely, means all energy loss. That energy converted into the heat. So if I am saying what is the total heat produced? What is the total heat produced? What is the total heat produced? That is a half mv square. Okay, if in the joule, if you are writing in calories, so half mv square by J. Everybody is getting or not? Initial energy of the bullet is half mv square. Bullet is stopped completely means all energy get destroyed. It converted into the heat. Okay, so half mv square joule or half mv square by J calorie. Okay, so total heat produced is the half mv square, but it is equally shared by the bullet and the wall. Means 50% remain in the bullet, 50% goes to the wall. Okay, so how much energy remain in the bullet? How much heat produced in the bullet? How much heat remains in the bullet? How you got 160? I have not given the mass. So total heat produced, we can say total heat produced, that is equal to what? Half mv square initial energy. Okay, and heat remain in the bullet. What I can say? Total is this. Half is shared by the wall, half is shared by the bullet. So what you will get? 1/4 mv square. Up to this, any problem? Okay. So what is the heat in the bullet? Heat in the bullet is a 1/4 mv square. And that heat is changing the temperature of the bullet. This heat is changing the temperature of the bullet. So for the change in temperature, heat we always equate with ms delta theta. Yes or no? For temperature change, always heat we write as a ms delta theta. So how much heat produced? 1/4 mv square, and that will be equal to the ms delta theta. So we can say 1/4 mv square, that is equal to ms delta theta. Now m and m cancel out. So one thing we can say, delta theta is equal to v square by 4s. It means change in temperature does not depends on the increase in temperature, does not depends upon the which quantity? Mass, because mass is getting cancelled out. Okay, now delta theta value we have to find. So delta theta, what we can say? V square. V they have given how much? 200. 200 into 200 by 4 into specific heat I have given 125. So this 4, 2 and 2 cancel out. So what we got? 10,000 by 125. So 125, 8 is a 1000, so 80. So what you got? Delta theta is the 80 degree C. What is the 400? What is the 400? I think answer we are getting 80. Done. Okay. Okay. Completed. Okay. Okay. So this is about the Joules law. Now, in a thermodynamics, we have to first know what is the thermodynamic system, what is the thermodynamic variable, what is the surrounding. So no need to write, just listen only if your wish, if you want to write. So first, if I am asking what is the thermodynamic system, what is the thermodynamic system? So thermodynamic, when we are talking about the system, so system is basically here we will discuss about the gas. So we can say the thermodynamic system is what? That can be represented in the terms of pressure, volume, temperature. Okay. So what is a thermodynamic system? That we can express in the terms of pressure, volume and temperature. Like gas enclosed in the container. So if a gas is enclosed in the container, then we can write the pressure of the gas, we can write the volume of the gas, we can write the temperature of the gas. So this gas enclosed in the container we can take as a thermodynamic system. Yes or no? Okay, so this is the thermodynamic system. Now thermodynamic state variable. What is a thermodynamic state variable? So thermodynamic state variable is what? Like suppose the gas you have, it is enclosed in the container. Okay, so at this position you will write the pressure of the gas P, volume of the gas V, suppose temperature of the gas T, mass of the gas M. Okay, now when you take the piston from one position to another position, then what will happen? Pressure, volume, temperature, mass, pressure, volume, temperature may change. Maybe gas is leaking out, so mass will change. So what is the meaning of state variable? So different state, like here one state of the gas I am writing when this is in the piston is in this position. So we are writing the pressure, volume and temperature and mass. Now I shift the piston another position. Okay, so we will write the another pressure, volume, temperature and mass. So these are what we are representing, these variable in the different state. So pressure, volume, temperature, mass, these are called the thermodynamic state variable. At the different state, these variable have the different values. Getting my point or not? So thermodynamic state variable means how we will represent the state of the gas. So state of the gas you will represent by the pressure, volume, temperature, mass. Understood? So what is the thermodynamic state variables? Pressure, volume, temperature, mass, internal energy and entropy we can also add in that. Okay, so thermodynamic state variables are pressure, volume, temperature, mass, entropy, internal energy. All this we can take as a state variable. Everybody got or not? Okay, so thermodynamic system, thermodynamic state variable. Okay. Okay. Now I can say so thermodynamic state variable, so pressure, volume, temperature and mass. This we can categorize into the two type. Okay, one type I will write, other type you will say. Okay, so state variable we can divide into the two type. One is the intensive. So what is the other? Extensive. Okay, so one is the intensive, so other will be extensive. Okay, so what is the difference in these intensive and extensive? So extensive, from the extension we can say it depends upon the size of the system. Extensive is what? It depends upon the size of system. Okay, Okay, so intensive. So what the intensive we can say? Intensive does not depends upon size of system. Are say yes or no? Extensive is from the extension we can say. So extensive depends on the size of the system. Okay, and intensive does not depends on the size of system. Okay. Now I will write few variable. You will say which one is intensive, which one is extensive. Okay. So suppose I am writing the variables P, V, T, density, internal energy, and mass. These 6 variable I am writing, and I am asking which one is intensive, which one is extensive. Okay. So how to decide? Like suppose I have the one container. Okay, any gas is enclosed in that. Any gas is enclosed in this. Okay, so gas has some pressure P, volume V, temperature T, mass M. Okay. Now suppose I just put the one boundary in between and I separate this container into the 2 equal half. I separate this into the 2 equal half. Okay. Then if you are dividing into the 2 equal half, which quantity will change, that you have to decide. Okay. So initially the gas was enclosed. Okay, pressure P, volume V, temperature T. Now it is divided into the 2 equal half. I just put the one divider in between. Okay. What is the effect on volume? What is the effect on each part? Volume. Half. So volume depends on the size or not? Volume depends upon the size or not? It depends. Okay, so volume is intensive or extensive? Volume is intensive or extensive? Extensive. Okay, so volume is extensive. Okay, mass. Mass. Each part mass become half. So mass is also extensive. Okay. What about pressure? Pressure. Pressure. Initially pressure was P. When I divided, I am not changing the, I am not applying extra force, I am not putting extra, so pressure will be same. Pressure difference will not be there. I just put the one boundary in between, no any extra force or came, so pressure will be same. So pressure is intensive. Okay. Temperature. Temperature same. Okay, so temperature is also intensive. Okay. Internal energy. Internal energy. Internal energy same. Internal energy is what? What is the formula? We have learned the internal energy formula. F by 2 nRT. Remember? Internal energy formula. F by 2 nRT. F is not changing. Temperature is not changing. R is constant. But mole is becoming half or not? Mole become half. In each part, mole will be half. Mole become half. So internal energy also become half. So intensive or extensive? Extensive. So internal energy we will write extensive. Okay. And density? Density same. Density same. Why? Because suppose this is a classroom. Classroom half you divide, but the distance between the student will remain same. So density will, otherwise we can say what? Density is the mass by volume. Mass become half, volume become half. So that's why density will remain same. Okay. So density will be intensive. Okay. Completed. Okay. Now we have used this word surrounding, surrounding system, surrounding system, surrounding. So what is the meaning of surrounding? So we say that system plus surrounding, that we can write as a universe. Okay. So like suppose I am taking this, where you are sitting, suppose your room is the system. Your room is a system, so rest of the universe is what? So your surrounding. Okay, so we can say what? Suppose from the universe I take small part of the universe. I take a small part of the universe, so that part I can take as a system. So rest part of the universe will be the surrounding. Okay, that's why I'm saying system plus surrounding is equal to universe. Okay. Okay. So we have learned the three types of thermodynamic system. So types of thermodynamic system. So I think most of you know that closed system, open system, and third one is the isolated system. Okay. So closed system means what? Suppose you have the gas that is closed by some piston or, okay. We have a gas that is enclosed by any piston. So if I put this gas, this system in a surrounding, so there is a outside is that surrounding. If I put this system, can it exchange the mass with the surrounding? It cannot exchange the mass with the surrounding. Why? Mass cannot go inside the gas because it is closed and it cannot go out of the gas. So that's why mass exchange will not take place. But heat exchange may take place. Heat exchange may take place. Suppose the gas is at higher temperature and the outside is a lower temperature, so heat can flow through the container wall. Okay. So heat exchange may take place, but mass exchange does not take place. Yes or no? So in the closed system, we can say delta M is equal to 0. Means mass no exchange, but heat exchange may take place. Yes or no? In open system means what? This is an open container you can take. So mass exchange may take place as well as heat exchange will also take place. So both exchange may take place. Okay. So open system, both may exchange. Isolated system is what? Go out of the universe. Go out of universe. No, when you go out of the universe, no surrounding is there. No surrounding is there. So from to whom you will exchange the mass or to whom you will exchange the energy. Okay, no surrounding is there. So it means no heat exchange, no mass exchange. Okay, so no exchange of mass and energy. Okay, so remember this system definition. We will discuss more about system when we will discuss the first law of thermodynamics. Okay. So closed system, mass exchange will not take place. Open system, both exchange may take place. Isolated system, no exchange of mass and energy. Okay. What is a thermal equilibrium? What is a thermal equilibrium? Thermal equilibrium. Temperature same. Okay. Temperature, we have learned that when the two bodies are the different temperature you kept in contact, so they will exchange the heat till they reach to the thermal equilibrium. Okay. So thermal equilibrium means temperature same. Okay. So first one is the Zeroth Law of Thermodynamics. Okay. So Zeroth law, no any mathematical relation is there. That is only the statement. So we have to know the statement, maybe because they can give the statement and they will say this statement is the law of conservation of energy, law of conservation of momentum, like that they can say Zeroth law of thermodynamics, first law of thermodynamics. So we have to know the statement. Okay. So Zeroth law of thermodynamics is what? So suppose I am taking two systems, A and B. There are the two gaseous system A and B, and they are at the different temperature T1 and T2. Okay, and they are separated by the non-conducting wall. Okay, so they can exchange the heat or not? if the two gaseous system I have A and B, their temperature are different, but they are separated by the non-conducting wall. So they can exchange the heat or not? No. Why? Heat cannot go through the non-conducting wall. So their temperature will be different. So they are not in the thermal equilibrium. Yes or no? Okay. Now suppose another container C I put on them like this, and they are separated by the conducting wall. Okay. They are separated by conducting wall. Now A and C can exchange the heat. Yes. B and C can exchange the heat. Yes. So what will happen? A and C will exchange the heat till their temperature become A and C will exchange the heat till their temperature become equal. B and C exchange the heat till their temperature become equal. Yes or no? So after some time, what will happen? Temperature of A will be equal to temperature of C, and temperature of B will be equal to temperature of C. Okay. It means temperature of A is equal to C, temperature of B is equal to C. Then what I can say? Temperature of A and temperature of B will be equal to temperature of B. Okay. Then it means now A and B came in the thermal equilibrium. Yes or no? So what we can say? If two different bodies are in thermal equilibrium with another body, two different bodies are in thermal equilibrium with the another body, then both body will also be in thermal equilibrium. Means A and B are in thermal equilibrium with C. So A and B will also be in thermal equilibrium. Understood? So you have to remember the statement. You will remember now? If two bodies are in thermal equilibrium with the third body, then both body will also be in the thermal equilibrium. Okay. Now after this state, suppose I remove this wall. I remove this wall and I replace this wall by the conducting wall. What will happen? After some time now, I replace this wall by the conducting wall. What will happen? Nothing will happen. Why? They came at the same temperature. Now the heat exchange will not take place. So if whether I replace this wall after some time, I replace this wall by the conducting wall, no heat will flow because all came in the thermal equilibrium. Okay. Okay. This is the zeroth law. Now next is the internal So what is the internal energy of a gas? What is the internal energy of a gas? Kinetic, sum of all energies. Basically, it is the sum of all energy. That is a more appropriate. Means we can say the sum of kinetic energy and potential energy of the gas is the internal energy. Okay. Just wait, Gayatri. So internal energy means what? If I am talking about the internal energy, then we can say what? It is the sum of kinetic energy and potential energy. But one more thing we have learned, for the ideal gas, potential energy of the interaction is zero. Yes or no? For ideal gas, we have learned potential energy of the interaction is zero. Why? That was the assumption of the ideal gas. Ideal gas molecule does not apply the force on each other. So due to their interaction, they don't have any interaction in the terms of forces. So their potential energy will be zero. Yes or no? This we have learned in the kinetic theory of gas. So internal energy of the gas means it is a sum of kinetic energy and potential energy. But for the ideal gas, potential energy of interaction is zero. Okay. But suppose I have the non-rigid molecule. I have the gas non-rigid molecule. Non-rigid molecule means it can vibrate. Yes or no? So like suppose just imagine I am taking the molecule I am taking like a spring. You can imagine like suppose these are the molecules. Okay. These molecules do not apply the force on each other. These molecules do not apply the force on each other because ideal gas molecule, it is the assumption. So they are not applying the force. So what is their potential energy? Zero. Okay. But molecule can vibrate. Molecule can vibrate. So for the vibration, it has that vibrational kinetic energy, like when the spring get compressed and when the spring get elongate, it will have the potential energy. Yes or no? Okay, so molecule and molecule, no force is acting. Molecule and molecule, no force is acting. But due to the vibration, it may have vibrational potential energy. Yes or no? Okay, Gayatri, vibration kinetic energy, no need to write. Directly we can say it is a kinetic energy plus vibrational potential energy. So, but with the potential energy, there is a condition. Means it is a rigid or non-rigid. But if I am asking what is the internal energy of the gas, then we can say it is a sum of kinetic energy and potential energy. Ideal gas, potential energy of interaction is 0. Okay, no problem. But it may have potential energy due to the vibration. Okay. Getting or not? So if I'm asking what is the internal energy, then we will say what? It is a sum of kinetic energy and potential energy. Now understood or not? Okay. So internal energy we can say that is a sum of kinetic energy and potential energy. And we know that for ideal gas, potential energy of interaction is 0. Interaction potential energy will be 0. Okay. But it may have vibrational potential energy. Completed? Okay. Next, we have learned the formula of the internal energy. What? U is equal to? What is a U? 2, 3 formula we have learned. F by 2 nRT. This we have learned. Is this formula is valid any particular case? Or suppose I am saying delta U. Delta U, what we will write? F by 2 nR delta T. Okay. Is this formula applicable for any particular case, any particular process, any particular gas? If I am saying delta U is equal to F by 2 nR delta T, I said that this formula is valid for the particular process. No, it is the same for all, because the change in internal energy if I am asking, so we will directly say F by 2 nR delta T for the same gas and the given number of moles. This is the formula valid for all the process. Okay. If you remember, this I have taken equal to the NCV delta theta, NCV delta T, because heat given at constant volume utilized on the change in internal energy only. Remember last class I discussed. So this delta, from that I got the formula CV is equal to FR by 2. By equating that I got the formula CV is equal to FR by 2. So another formula of the delta U, I can say what? NCV delta T. Okay. Yes or no? So if I am saying delta U is the NCV delta T, delta U is equal to NCV delta T, it is applicable for all process or it is applicable for only constant volume process? That I expect. Constant volume, if I am asking the heat, at constant volume, then you will say Q is equal to NCV delta T. So heat at constant volume, you will apply NCV delta T. So heat I can write NCV delta T when I have the only constant volume process. But this delta U we are getting what? This delta U is applicable for all process. This I write this. So heat will be different. Heat, if I am writing for the different process, that will be different. But here I'm NCV delta T is not the heat. NCV delta T is the delta U. Okay, so this will be applicable for all process. It is not like heat is the NCV delta T. It is at constant volume. But NCV delta T we can use for all process. Understood is not or not? Okay, so don't think that NCV delta T is the applicable for only constant volume. Heat Q is equal to NCV delta T is applicable for only constant volume, but this is applicable for all process, because by equating these two I got the CV is equal to FR by 2. Okay, so applicable for okay. Any other formula? CV already we know that if we know the gamma, so CV we can write R upon gamma minus 1. So that is a different, like same formula you will get. Any other formula we can get? Suppose we don't know the temperature change. We don't know the initial and final temperature. We don't know the delta theta. Then what? We know the pressure and volume. So how we can write the delta U in the terms of pressure and volume? So if you see this, delta U is equal to F by 2 NR delta T. Delta U is the F by 2 NR delta T. What is the NR delta T I can write in the terms of pressure and volume? NR delta T, what I can write in the terms of pressure and volume? NR delta T. This I have already discussed. NR delta T is not the P delta V. Most of the students think that NR delta, because before I have explained this, NR delta T is not the P delta V only. Okay, because if I write the ideal gas equation, so P1 V1 is equal to NR T1, P2 V2 is equal to NR T2. When you subtract, so NR T2 minus T1, that is NR delta T. What you will get? P2 V2 minus P1 V1. Okay, so NR delta T we will not write P delta V. NR delta T means what? P2 V2 minus P1 V1. Understood or not? Okay, then delta U I can write as F by 2. NR F by 2. NR delta T I can write P final V final minus P initial V initial. Means 2 I am taking final. 1 to 2 means 2 I am taking final, 1 I am taking initial. So P2 V2 means P final V final minus P1 V1 P initial into V initial. Yes or no? Okay. One thing, at constant wall pressure, if pressure is constant, it means suppose I am taking P final is equal to P initial is equal to P. Then what you can write? PF and PI are equal. Pressure is constant. Then P we can take common. Then you will get V final minus V initial. Then V final minus V initial, what you will write? P delta V. So at constant pressure we can say P delta V is equal to what? NR delta T. So NR delta T is equal to P delta V. We can write at a constant pressure only. Understood or not? Okay. Okay, then. So here we can write as a delta U is the F by 2 P delta V at constant pressure. Okay. Can we write use the Ashwak? How you can write use the NCP? Then why I said the NCP delta T is applicable for all process? If you can write NCP delta T. So for all process, U internal energy, what you will write? Delta U, you will write NCV delta T. Then how you can write U is equal to NCV delta NCP delta T? First we are saying for all process delta U is the NCV delta T. Then now you are asking, you can write delta U is equal to NCP delta T. How? When you are writing CV, then how you can write CP? Okay, so if you remember, I said heat given at constant pressure, constant volume. So when you are giving the heat, okay, that heat is not doing any work. That heat is not doing any work. That heat is only changing the internal energy. That heat is only changing the internal energy. Okay, then heat will be equal to delta U. Heat will be equal to delta U. Okay. Now delta U, what we can find? Delta U is equal to, I am giving the heat at constant volume. So that delta U I can write NCV delta T, because heat I am giving at constant volume. Now delta U, what I got? NCV delta T. Okay, but suppose now you got delta U is the NCV delta T. Now I am giving the heat not at constant volume. I am giving the heat at constant pressure. Suppose I am giving the heat at constant pressure now. So Q, what I will write? Q will change. Q I will write as NCP delta T. If I am giving the heat, now I am giving the heat at constant pressure. So heat I will write NCP delta T. So in this heat, some part will change the internal energy, some part will do the work. We learned in the first law of thermodynamics. Some part will change the internal energy, some part will go in a work. Which part will change the internal energy? This. Rest part will go in a work done. Getting or not? So change in internal energy always will be what? NCV delta T. Whether the process is the isochoric or not. Means constant volume or not. Understood or not? Okay. So means for whatever the process, heat will change, work will change, but delta U will be always equal to NCV delta T. Okay. Okay. So this formula of the delta U is over. Okay. If I am saying the temperature is constant, what is the change in internal energy? If temperature is constant, what is the change in internal energy? 0, because delta T is equal to 0. It means temperature is constant. Then delta U, what you will get? 0. It means U will be constant. Okay. If temperature is increasing, so internal energy will increase or decrease? Temperature is increasing, then internal energy will increase or decrease? Increase. Why? Delta T is positive, so delta U will be positive. Delta U positive means U final is more than U initial. It means internal energy will increase. If delta T temperature is decreasing, so temperature decreasing, so delta T negative. Delta T negative means delta U negative. Delta U negative means internal energy is decreasing. Okay. Completed. Okay, done. Now last one more point for the internal energy. So first I'm writing internal energy does change in internal energy does not depends upon path. It depends upon initial and final state. And for cyclic process, delta U is equal to 0. Okay. So change in internal energy does not depends upon the path. It depends upon the initial and final position. So if initial and final position coincide, means cyclic process. Again, it reaches to the same position. So for cyclic process, change in internal energy will be 0. Okay. Now how I can? So suppose I am taking the two different state. At any state A, pressure is P1, volume is V1, temperature is T1, and then it is gas is taken up to the state 2. State 2 pressure is P2, volume V2, temperature T2. Okay. So suppose gas is taken from the state A to the state B by A to the B by the different path. Suppose like this, it is going path 1, then it is going to the path 2, and it is going to the path 3. Okay. for all the paths, heat will be different, work will be different, but for all the path, initial state is what? A, and final state is the B. Initial state is A, final state is the B. So change in internal energy for all the path will be same, because the change in internal energy does not depends upon the path. It depends upon the zero, how it depends upon the initial and final state. So initial state for all is A, final state for all is B. So what I will write, delta U1, change in internal energy for the process 1 is equal to change in internal energy of the path 2 is equal to change in internal energy for the path 3, and that will be equal to what I can write? All are equal. So delta U means what? Final minus initial. It means you will write UF minus UI. What is the final state? B. So you will write internal energy at B minus internal energy at A. Understood or not? So work will be different, heat will be different, but change in internal energy will be equal for all. Why? Because the initial state for all the paths process is the A, final state for all the process is the B. Suppose I am saying we are going from B to A. B to A, what will be the change in internal energy? Then it will get reverse. Reverse means negative you will get. Means if I am saying UA minus UB, means path is the A to B. Delta U is equal to what you will write? UB minus UA. Then if you are going from B to A, so B to A means final is the A, initial is the B. So delta U, what you will write? UA minus UB. Now in this, what is the relation? Delta U1 is equal to minus delta U2. Yes or no? Delta U1, what you are getting? UB minus UA. Here delta U2, what you are getting? UA minus UB. So what is the relation between delta U1 and delta U2? Delta U1 is equal to minus of delta U2. Completed? So work and first law of thermodynamics is remaining. So first you will say one problem. If I am asking, in which case we can get the change in internal energy is zero? In which case we may get change in internal energy is zero? In which option we may get change in internal energy is zero? 3. In which process we may get change in internal energy zero? Four. All you can get. 1. Okay, listen. Process 2. First I am saying the 2. In a 2 you can see A to B. So here when the pressure and volume condition we know, so change in internal energy we will take F by 2, P2 V2 minus P final V final minus P initial V initial. Remember that formula I discussed now. Okay. So if I'm taking the option 2, final state is the B. So you will write pressure into final volume minus initial pressure into initial volume. So final and initial, it is a constant pressure. Constant pressure means P is the same. So what you will write? P2 V2 minus P1 V1, you will write P delta V. Okay, and here delta V is non-zero. Why? Volume is increasing from A to B. Are yes or no? From A to B, volume is increasing. Okay, then you will get the delta U 0. You will get delta U 0. No, why? Here P delta V is non-zero. Because delta V is non-zero. Here A to B volume is increasing. So in this case, delta U, you can write what? F by 2 into P delta V. Now delta P is non-zero, delta V is non-zero, so you will not get delta U 0. So answer is not 2. Okay. In the 2 we cannot get. In 3 also you can see final pressure, final volume. Final pressure and final volume is more than initial pressure and initial volume. So means P2 V2 will be more than P1 V1. P2 V2 will be more than P1 V1. So in that case also we will never get 0. Are yes or no? At B, pressure more, volume more. At A, pressure less, volume less. So product of the pressure and volume at B will be more than pressure and volume product at A. So that's why in this case also we cannot get 0. First case, we may get. First, I'm not saying always. First case, we may get. Like suppose A, pressure is the 2 unit, volume is the 1 unit. And at B, volume is the 1 unit, volume is the 2 unit. So what is the product you will get? 2 into 1, 1 into 2, 2. 2 and 2, P2 V2 and P1 V1. Both are 2. So what the difference you will get? 0. So you may get. I'm not saying always, but we may get 0 in a first case. Understood? Okay. So up to the internal energy maybe, because actually I thought that I will take the extra class today, but in a boys class syllabus has only completed up to the CP and CV. Even that is also not started, so it will complete in the maybe in the evening. So we can take up to the this only internal energy. Okay. So in the so I think I thought that I will take the class, but I think not required now. Okay, so you have to do up to this only. Question is what? Question I said what? In which case, in which process you may get change in internal energy 0. Okay. Okay then, bye bye. In third case, temperature is constant. How you can say, Siddhi? How you can say temperature constant? P directly proportional to V. P directly proportional to V, then how you can say temperature constant? P inversely proportional to V, then you can say for a given gas, P inversely proportional to V, then temperature you will get constant. But third case, you are getting P directly proportional to V maybe. How you can say? Understood or not? So we cannot say that temperature is constant in the third case. Okay. 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 Bye bye. Bye bye.